We're not getting any sound on the remote.
Will, can you hear me now over Zoom?
Yes, I can hear you now, Sugata.
Okay, great.
I'll delete my Slack message about this then.
How about now? Can you hear me? Because I'm using a different mic.
Yeah.
Yes.
Okay, great. Thanks. We're fine. Okay, welcome everyone. Thank you all for coming. We thought we'd give it a few minutes because the session that happened in this room beforehand overran significantly. So hopefully you guys have had a chance to have some tea and coffee. So let's make a start. So this is the low surface ground of science with LSST session. And we have 4 talks. The last talk is remote. But our first talk is by Emery Watkins from the University of Hertfordshire. And he's going to tell us about the risks to LSST's discovery space that might be posed by sky subtraction.
Hello, everybody. Good afternoon. So yes, welcome to the LSP session. I'm going to be kicking things off today by discussing a data reduction procedure, which is the removal of the night sky from your images and how it can potentially go wrong. And also, on a more positive note, some work that we've been doing trying to make sure that it doesn't go wrong for LSP science. We've done a lot of this work in conjunction with the data management team, so I want to thank them for their assistance and their patience with us. And let's go ahead and move on. And this thing turned itself off. Let's see. Yeah. Oops. Okay, now it's working. So let me just begin with a quick introductory slide about LSP science. If you're not familiar, LSP is a very broad term, covers a lot of things, everything from basically dwarf galaxies to things like tidal streams and so on, as well as non-galaxies related things like galactic cirrus, comet tails, whatever you like. It's also a fairly new field. It really wasn't accessible until maybe the past couple of decades when data reduction technology and also telescope technology kind of was able to access this regime. So at the moment, it's pretty much dominated by very small scale targeted surveys done by small telescopes, typically of a single galaxy or a single galaxy cluster or group. So LSST presents a great opportunity to expand LSB science because from a calculation done by Peter Melchior earlier this year, the 10-year depth in surface brightness, at least optimistically for LSST, is somewhere around 30 magnitudes per square arc second, which is something like 5 magnitudes per square arc second deeper than SDSS, which is obviously a survey of similar spatial scale. So if we get even close to this number, which we should be able to, LSST will be the first survey to produce really statistically robust samples of things like dwarf galaxies, including very low mass ones in the local universe, like this one that I'm showing over here, recently discovered by Dave Sand's group, as well as high redshift dwarfs, tidal features, even maybe some around dwarf galaxies, intracluster light, intergroup light, and then also maps of galactic cirrus and multi-band optical imaging, which could be useful as well. So what this all means is that LSB, being such a broad topic, comprises a fairly large fraction of LSST's potential discovery space, assuming, of course, that the LSB flux is actually preserved by the pipeline. So I thought I would start this off by scaring all of the LSB science people in the room and showing this image, which was gifted to me by Javier Roman. What this is showing is 2 images of the same part of the sky. The left image is an INT exposure taken by Javi and reduced using his own custom pipeline. And you can see all this lovely diffuse light, these galactic cirrus clouds. And the right image is the exact same field, but as seen in the DECAL survey. So basically post their sky subtraction routine. And you can see that if you do a sky subtraction that's not tailored to LSB, you run the risk of removing basically all of it from your images. With regard to LSST though, they are using a much more friendly to low surface brightness pipeline at the moment. Here's a quick summary as I understand it. And of course, if anyone from DM wants to correct me, feel free. But I believe what's happening is it's done in 3 stages. There's first an initial very aggressive sky subtraction, which is done, I believe, mainly to aid with source detection on the visit level images. This is not used in the final sky subtraction. It's put back in the images. And then a second order sky subtraction is done using a full focal plane model by essentially binning the full focal plane into very large, what they call superpixel bins. For HSC PDR2, I believe it was 1024 by 1024. It sounds like for LSST right now, they're using 8192 by 8192, which is larger than a CCD. So they bin the image into these big pixels so that it covers across chip gaps, and then you fit some kind of a model for the full focal plane and subtract it off as the sky, which gets rid of all of the large scale kind of time variable sky from your image. And then finally, because telescopes have optics and filters are not perfect, you have these patterns imposed by things like light concentration as well as transparency differences across the field of view in the filter itself. And so they use these pre-made images, which they call sky frames, to scale that to the background of each individual exposure and then subtract off these smaller scale patterns imposed by the telescope optics. So this works quite well for LSB. It's certainly better than HSC PDR1, which everybody in LSB complained about. But we did do some tests by injecting synthetic sources into the pipeline a couple of years ago, just prior to the full focal plane sky estimation, just to see what would happen to the LSB flux. And what we found is that there are a few very subtle issues going on here. So what I'm showing on the right is this is a plot of the over subtraction among all of the model galaxies that we injected as a function of the isophotal surface brightness for the average model that we injected, at which that much over subtraction occurs. And so we found that starting at around maybe 26, 27 magnitudes per square arc second, we do start to see a systematic over subtraction of flux in the very faintest outskirts of the models that we injected, which seems to get worse the deeper that you go around a given model. And so you do end up with these very subtle dark over subtraction rings in the very lowest surface brightness regions of your typical model, which seems to be induced by the pipeline somehow. This is worse for very large objects like ICL, but it does seem to affect at some level everything that we injected. So given that, we started talking to a lot of LSP scientists and just try to figure out, in addition to doing our own tests using fully synthetic images, as well as using images that we had access to from previous observation campaigns, what is the best strategy to use for sky subtraction to avoid any amount of over subtraction, basically at any level? And in conducting these tests, I've identified one thing as being pretty much critical to any approach that you take, which is the masking. So the biggest issue here seems to be that you always run the risk of accidentally overfitting your skies and thereby including low surface brightness flux that you're interested in your sky model and subsequently subtracting it off. Whereas if you can somehow identify the LSP flux prior to modeling the sky and masking it out, then you lower the risk of that happening. This plot here is showing an interesting experiment I did regarding these superpixel ideas. So the basic idea behind a superpixel is you take a region of your image with some given dimensions, you mask all the sources within that region, and you take a clipped mean of the unmasked pixels as sort of the representative value of the flux in that particular box. So I just decided to test how sensitive is the clipped mean to unmasked low surface brightness flux. And what I discovered by just injecting fake galaxies and other things into images and then trying to get back the input sky that I was using in these synthetic experiments, I just tried to see how much do you have to mask the image in order to actually get back the appropriate sky value, the real one that I would put in myself. And I found this kind of behavior, which you see on the right, which is showing in a particular image, this is the fraction of unmasked pixels versus the depth of the mask in surface brightness at which I actually did achieve that convergence. So at which I was able to use the clipped mean to get back something very close to the input sky value. And we have this sort of diminishing returns behavior where the more pixels that you have to mask while measuring a clipped mean, the deeper your masks actually have to go in order to get back the right value. The converse of this is that if you're using too shallow of a mask, then your clipped mean is overestimating the flux in that box, and you're therefore overestimating the sky, which again puts you at risk of mild over subtraction. So this brings up the question, a very common method used here is a polynomial fit sky model. So this brings up the question that has far more parameters than just a clipped mean. How dangerous is it to actually do a polynomial fit sky? So I did an additional experiment, again, using synthetic images where I tried to test this. I created a slew of model images with model skies with polynomial orders ranging from 1 to 10. And then I would mask the images after injecting fake sources, fake galaxies, stars, things like that. I would mask them down to different surface brightness levels and then refit the sky using the same polynomial function and just see what do the residuals look like for different mask depths. So what this plot is showing is these are the amplitude of the residuals. In this case, it's a very crude measure. It's just the maximum minus the minimum value of the residual image after fitting the sky versus the mask depth that I used. And each of these curves is a different polynomial order. So what you can see here is that you can actually do this somewhat safely if you use a low polynomial order sky. So anything from 1 to maybe about 3, you don't tend to risk too much overfitting. For convenience, I've drawn the LSST 10-year depth as a red line here. And so if you look at where these different curves intersect, you can see that for LSST, it seems like you can get away with upwards of maybe a 4th order polynomial fit if your masks are deeper than about 28 magnitudes per square arc second, which is actually fairly feasible. So that's kind of a nice number to have in mind. And it also means that while polynomial fitting can be a bit dangerous, it is still a feasible option as long as you take some care with the masking procedure. But just for fun, I also looked at I also looked at a couple of other alternative sky subtraction routines, which people have used. This one I'm calling chop and nod, which is after the infrared technique used that it's sort of based on. This has been used successfully in CFHT imaging as part of the Elixir LSP pipeline. The basic idea here is to take a handful of exposures that were taken close in space and time, but dithered with respect to each other, and just combine them together and then apply some kind of a smoothing to reduce the noise. And that produces an average sky for that range of exposures. The benefit here is that it's completely model free. So if you have a lot of small scale kind of high frequency structure, then you don't have to worry about your second order polynomial not picking it up and accurately measuring it. I experimented with this as well using synthetic images. I just created a slew of images, all with exactly the same model sky. So assuming the sky is constant, but dithered sources, dithered fake sources. And I would combine them together and smooth them and see at which point it converges. And what I'm showing on the left here, in the upper left, is the difference between the mean value of the sky that gets produced after combining these frames compared to the input model sky as a function of number of exposures combined. And I managed to reproduce what was reported in Duke et al. 2015, which is that it does converge after about 8 to 12 exposures. So you really don't need that many to get back a decent representation of your sky. But it is sensitive to LSB flux. So if this was working perfectly, it would converge to a value of 0. But instead, you see it converges to a value of about 0.5. So it means that there's some kind of a low surface brightness pedestal level that's left behind after doing this. So if you do use this method, you still need to do some kind of a masking and secondary sky estimation to take that back out. The other biggest issue is the risk of adding noise. Because you're only combining 8 to 12 exposures, you can beat down the noise a lot by smoothing it, but you're never going to get rid of it entirely, which is what this lower left panel is showing here. This is the difference between the standard deviation of the output sky versus the model sky that I input. You can see it has this sort of 1/√n behavior, and you never quite get to 0. So when you do subtract these skies, you are adding noise onto every individual frame that you subtract them from. And for well-behaved skies, this actually degrades the limiting surface brightness of your final generation coad compared to just a polynomial fit plus masking procedure. So I would say if we use this one, we would have to use it with care. And then finally, the last thing that I was testing was a kind of novel algorithm, which I believe was originally proposed by people from data management. The idea here is to create an initial sky subtracted coad using some subset of your exposures, align that to your individual exposures, scale it in flux to the proper photometric 0 point, maybe do some PSF matching, and then subtract it off of those exposures so that you remove all the stars and galaxies and galactic cirrus and everything that messes up your sky model without having to mask really. So I put this through another round of tests, and I've identified another couple of potential issues with this one too. The first one, which I think might be the most critical one, is that it seems like if you make any mistakes in your creation of your initial coad, so if there are sky subtraction related artifacts on the first coad that you create, they will propagate infinitely. And therefore your sky model subsequently after subtracting the coad pretty much doesn't converge. And I'm showing this explicitly on the right here. These are 3 fit parameters for a single frame from Nordic optical telescope data that I used to test this. Each of these is a different iteration of this procedure: create a coad, subtract it, measure the sky, create a new coad, etc. And you can see that for each iteration, the fits just continually change. They never converge onto a single value. And this is after 10 iterations, which that's 10 coads. It's a lot of processing time. So I'm not quite sure how to work around that. The other issue, you can do this model free. You don't have to fit the coad subtracted images. You can just bin and smooth to get rid of some of the noise. But then we run into the issue that I mentioned in the previous slide, where you start degrading your limiting surface brightness by adding noise from your sky models. And finally, the last thing that I noticed, which is fairly recent development, is if you have a very subtle sky scattered light artifact, say 1% the scale of your night sky, your fitting is going to ignore it if you use a low order polynomial. And also the binning and the smoothing is going to kind of bin and smooth over that artifact. So these things as well, these really subtle scattered light artifacts, which most people don't care about, but which we as LSB scientists do, tend to persist even when doing this method. So given all that, it kind of feels to me at the moment like the simplest approach, masking plus polynomial fitting, might actually be the best approach in terms of compute time and accuracy of your sky subtraction. So that's all I have. So I think I'm probably out of time, so I'll just leave up my summary and take everybody's questions. Thanks for listening.
Okay, questions for Aaron? Wait.
Hi. When you do the quad, there's an effect of resampling. Do you understand what is the effect of resampling on the sky is
Sorry, the
coming.
audio in here is,
When you said that you did the exercise on the quad image as well.
yeah,
So when you quad, there's an effect of resampling there.
of resampling?
Yes.
I suppose so, yeah.
Yeah. So what's the effect of the resampling on the estimation? Is that understood?
The effect of the resampling, I'm not sure I fully understand the question.
Um,
The effect of the resampling on the fit parameters?
Yes, well, because you estimate the sky on the quad image.
You know, actually, that is something I haven't thought about.
The-
So I'll consider the impact of that. I wonder if it isn't having an impact on the fact it's not converging. That's a really good point.
Yeah.
Okay, thank you for bringing that up. Yeah. So,
Okay, any more quick questions for Aaron? before we move on? Okay.
Yeah,
on Zoom.
Is there someone?
yes,
Okay, I'm not sure who you are, but go ahead. ask
okay. Hi, this is Tony Tyson. Yeah, there's another effect which we studied in a couple of papers, and that is that the very first stage where you try to detect everything just to get the big picture and then mask them and subtract. That's subject to not detecting a lot of extremely faint galaxies that are below your detection level in the first pass. And there are actually quite a lot of them by the time you get down to around 28th and fainter. And that gives an immediate sky offset issue right from the very beginning. The good news is that this can be estimated because this is the extragalactic background light due to undetected faint galaxies around 29th and fainter. So a model of that, which is pretty isotropic, should work as long as one can account for intervening dust absorption.
Yes, that is always one of those concerns, is what do you do about the cosmological background? I guess I would wonder, I don't know the answer to this. I'm just wondering out loud, how was that background measured? Because I'm assuming that from past surveys where the sky subtraction obviously varied from survey to survey, that would probably affect that measurement somehow and therefore the model. Is that correct, do you think?
Yeah, all of the observations are consistent so far, modulo this dust issue, with the extragalactic background light being pretty much, due to galaxies, pretty much isotropic. So, so one can derive a model for that and fit the model to the number magnitude counts.
Okay,
And yeah, it works. We tried it.
okay, so then that would be a nice sort of second order thing to add in here to avoid
Yeah.
accidentally overfitting the background, is what you're suggesting?
Yeah.
Yeah,
It's
you're right.
actually, yeah, if you don't do that, one is limited to about 28th magnitude per square.
Okay, yep. Okay, thank you.
Thank you very much. So next talk. Oh, would you like to thank? Thank you. So next talk is Mireia Montes, and she will speak about unveiling the optical low super brightness universe with LSST, the Intracluster Light.
Thank you very much, Simona and Sugata, for chairing this session. My name is Mireia Montes. I'm a postdoctoral fellow at the Instituto de Astrofísica de Canarias in the Canary Islands. And today I'm going to talk to you about the intracluster light, why we care about intracluster light, and what, sorry. Oh. Why we care about intracluster light, why we are interested in LSST, and what we are doing to prepare for LSST. And probably we will, at some point, we will share the slides. Yeah. Okay. Good. So, okay. So to give you, an idea of why we want to why we want LSST for loss of brightness is that one of the surveys that have revolutionized our understanding of the universe is the Sloan Digital Sky Survey. So thanks to its area and to its large area, we were able to study the universe in a statistical way. However, it has a very important shortcoming, is that its depth, which is you cannot see here, but it's 26.5 magnitudes per square second in boxes of 10 per 10 arc seconds. So that means that our knowledge of the universe is biased towards things that are brighter than this limit. So basically, we are biased to things that are, bright and massive. But we know that there are things that are beyond. That are beyond what Sloan could observe. For example, if we look at clusters of galaxies, if we take deep images of clusters of galaxies, we start seeing this diffuse light that fills the space between the galaxies of the cluster. And this is what we call the intracluster light. So whenever it's possible, when we take spectra or when we use tracers of the kinematics of this light, like globular clusters or planetary nebulae, we can see that the velocity dispersion increases with radius until it reaches the velocity dispersion of the galaxies in the cluster. So basically, we can say that these intracluster lights are stars that are do not belong to any particular galaxy in the cluster, but float around following the potential of the cluster. So, but normally we don't have that information. So in images, what we see is that this diffuse light it appears as an excess of light above your the component that describes your brightest cluster galaxy. This light also shows an increase in ellipticity with radius, and sometimes it changes the position angle. So basically, we can say that that the intercluster light is a different stellar and kinematical component of galaxy clusters. So it's not linked, well, it's linked to the BCG, but it's not the same thing as the BCG. So why we are interested in studying this light? So we are interested because this light, its formation is linked to the interactions between galaxies in the cluster. So, over time, all these stars that are stripped from the interactions between the galaxies end up populating. Oh, yeah, sorry, it's a PDF. You cannot see the. So that was a video. So they end up, the stars that are stripped from the galaxies end up in this intercluster light medium, and they form this diffuse light. And if you are not, like over time, they form this light. And of course, by looking at the properties, of this intracluster light, you can trace what happened in the cluster. But if you're not interested in what happens, like the assembly history of clusters of galaxies, maybe you are interested in the most sorry. This is not. Yeah, in the most massive galaxies in the universe, which are the brightest cluster galaxies or BCGs. Okay. Is this working? No, it's not working. It's not. Can we click again? Yeah. No. Don't look at this. That is not. Okay. So you might be interested in the most massive galaxies in the of the universe that are at the BCGs. So the simulations predict a growth rate of these massive galaxies that are not in line with what we see in observations. However, if in this case there's like some intracluster light formation, or if some of the mass, instead of going into the BCG, it goes into this intracluster light component, we see that the agreement between, like the growth rate of these galaxies from the simulations and from the observations agree much better. And of course, there's another aspect that we can use the intracluster light as a luminous tracer of the distribution of dark matter in clusters of galaxies. So, and why is that? That's because it's an extended component. It's around, hundreds of kiloparsecs, which is similar to the dark matter in clusters of galaxies. And also, these stars are not bound to any galaxy, so they are floating, following the potential of the cluster. And what is most of the potential of the cluster is dark matter. So, so basically, by using this intracluster light as a dark matter tracer, we can see how this dark matter distributes in clusters of galaxies. And also that this property can help us to find what is the splashback, where is the splashback radius. The splashback radius, if you are not familiar with it, is some sort of a physical boundary, physical edge of clusters of galaxies. So basically, you can understand it as, inside some radius you have a density of dark matter, of galaxies, or intracluster light, and outside this radius you don't have that much density or that much mass in dark matter or whatever. And you see here, when you do the gradient, you see here this bump of which signals this difference between what is your cluster and what is outside your cluster. So basically, like the intracluster light is very interesting. It can tell us a lot about clusters of galaxies, and we are also, seeing how this intracluster light correlates with different aspects of the cluster. It can tell us about the origin and therefore about what happened in the cluster. For example, we can study it's like the evolution of the ICL fraction of the quantity of light in this component respect with the total light of the cluster, and it tells us about the timescales of the interaction or the interactions that happen in the cluster. If we study the correlation with the mass of the cluster, we can see the processes that are involved in the creation of the intracluster light. And of course, we can use colors or ages and metallicities, the properties of the stellar populations, to see what are the progenitors of this intracluster light. But as you can see here, we really don't have that many points because, observing the intracluster light is very complicated. We don't have enough samples, enough clusters to actually see these correlations in detail. And that is why we are interested in LSST. So we are interested because it's the depth of LSST is going to be good enough to study the intracluster light. We are going to have enough clusters to actually, see how are these correlations, and also we are going to have multi-wavelength information to study the properties of this intracluster light. However, as I told you before, observationally, most of the time we don't have the information to separate intracluster light from the galaxies of the cluster. So, observers have come up with these different definitions of what is intracluster light. For example, we have the surface brightness cut. So any light that is fainter than a certain threshold, we we say that that is intracluster light. We have like this decomposition using two models, one describing the BCG and one describing this intracluster light component. And we have something that I call wavelet-like, which is basically doing some sort of filtering. So basically conserving what is like the most diffuse and extended component in an image. Sorry. But, you know, like when you want to study, you know, like these correlations with redshift or with mass, we see that this is a problem, you know, like these different definitions of intracluster light. And probably here you can see it better in this cartoon subplot here, that when you use a surface brightness cut, the evolution with redshift is much steeper than when you use this composite model, these two models that model your BCG and intracluster light. So, you know, like when trying to study that it's a problem. And that's why we are coming up with this low surface brightness challenge number 3. This challenge that is led by Sarah Braff is basically the observers and simulators measure the same quantity of intracluster light. So for this, in this challenge, what the aim is to figure out a way of, like the best way of defining the intracluster light. In this case, we have 4 simulations: the horizon AGN, the hydrangea clusters, LSST TNG, and magneticum. And with these simulations, we came up with a way with mock images. So we observers, 7 observers, can use our definitions of intracluster light. So, and also when we do that, we will compare with what the simulators are measuring. So this is some of the preliminary results that we have. We see here the color points are the measurements from the observers, and the open circles are the measurements from the simulations. So, and here we have different apertures, apertures for the simulators. And what you can see here is that what we are, as observers, what we are measuring is very similar to what the simulators are measuring between 100 in an aperture of from 100 to 1 megaparsec, which is kind of weird because here the observers are measuring the intracluster light in a very different way. So we have to look into that. Also, another thing that we are seeing is another thing that we are measuring is the fraction of ICL plus BCG respect with the total, you know, light of the cluster. And you see here that in this case the measurements agree much better. So it might be that the problem is how we define the inner parts of the cluster. So basically that's all I have. The ICL is a good tool to study the assembly of clusters, the most massive galaxies in the universe. And here what I have missing is that also to study the dark matter distribution in clusters of galaxies. And so check out that we are doing this challenge number 3, and we will come up, hopefully we will come up with a better definition of intracluster light for observers. Thank you very much.
Thank you, Mireia. Do you have questions? Maurizio.
I was wondering, in the context of LSST, when do you think the data start to be useful to probe really deep into the ACL? How long do you have to wait until the final stack, or after the first year is already good?
I guess that depends on how it's gonna, you know, like how it's gonna be taken. But probably for what we want to do for measuring the intercluster light, we have to wait till the 10-year depth.
Hello.
Someone is saying something?
So
Yeah,
there's
hi.
one
This
second.
is Tony Tyson. We are going to go even deeper than the 10-year depth in the first year in selected fields, just for this kind of exercise.
Yep.
That's the plan.
Yeah, that would be awesome. Thank you.
Thank you. I have a quick question. Another one.
So there's one question was Slack from Nushkia. How much of the stellar mass does ICO contain with respect to the mass of the cluster?
So that's a tricky question because normally when we measure it, it's on fraction of light because it's, normally what it's available because having deep enough observations, it's hard. So normally for the fraction of light, it ranges between 5 to 20% of the total light of the cluster. And in mass, I don't know, it might be like around that, but yeah, it's harder to say without information on at least the colors. So we can, assume like some sort of mass to light ratio.
Okay, thank you very much. I will ask you my question later. So let's thank Mireia again. And the next talk is Kanak Saha, and he will speak about faint galaxies from the AstroSat UV Deep Field.
Hello, everyone. I'd like to thank the organizers for giving me this opportunity to present the kind of science work that we're doing with AstroSat. This is a relatively new, but still like about 7 years old telescope that was launched by Indian Space Research Organization. It is a UV telescope, which is what we are using here. And I'm about to start my in-kind contribution. So I thought I will present some of the science results more or less on this. So. Okay. Here, what you see here are the two field of view of the UVIT, which is the UV telescope on board AstroSat. Each of them are 14 arc-minute in radius. So this was placed so that we get about, each of them have a 50 kiloseconds of observation flank. And we thought we would get about 100 kiloseconds on the good south. Yes. Okay, so it's the UVIT is a relatively small telescope. It has only 37.5 centimeter diameter aperture, and it has two co-aligned telescope, works one in the near ultraviolet and another in the far ultraviolet, and one can do simultaneous observations in this this is similar to like Galaxies, but instead of Galaxies, we have 5 filters in each of these far ultraviolet and the near ultraviolet telescope. And what I used is these 2 filters. Filters for observing the 2 field that I just showed. Between 2 successive frames, there are about 33 milliseconds. So in a good dump orbit, you have about 1500 to 1800 seconds of observation. So you have about 45,000 to 50,000 frames that are taken in an orbit. And of this, these are the frames which are stuck by the cosmic ray showers. And this we select and identify and remove from the pipeline, so directly, so that they don't affect the photometry later. This is the kind of the overlapping region that I just showed, and this is one the Muse Deep Field and the Hubble Deep Field you can see, and this is the AstroSat UV Deep Field in near ultraviolet, which works from the 2000 angstrom to 3000 angstrom. And if you quickly, I'll go through this. So this is the kind of PSF you have. We have about as a core, which is a MOFAT fitting with 1.4 arc-second FWHM, but it has a wing, you can see, go up to around 10 to 12 arc-second radius. And within an arc-second, we go about 27.9 magnitude at the 3 sigma detection limit, which is pretty good for doing the kind of science. So just in a piece of analysis that you do, this is a 240 arc-second by 240 arc-second piece of image on that. And this is where we run source extractor. And what I'm showing here is that there's a source here, which is our 26.6 magnitude, and for which we have a Muse spectra. And this is actually at the redshift 6, 5.9. And so here we estimate the background and the RMS, and also so what you can see on the right side is all the sources being detected just by traditional source extractor software. And then once it creates the background, just a source extractor background, we put in the apertures, and you can see, you can see these are the spurious detections, which is about 28 magnitude here. So we can very reliably estimate around 26 to 27 magnitude sources in the near ultraviolet. And we also estimate the background in a different way, because that's one of the interest. And for which we are just trying now to create a pseudo image, exactly popping up putting the point sources and noise, and trying to see if we can estimate the sky that we put in exactly. So this is directly relevant for our the faint source detection. Very quickly, I will go into one of the science results that came up from this study. So we looked at about 14 blue compact dwarf galaxy from the Chandra Deep Field South. These are all the 14 BCDs known. And BCDs are, as you know, they are very, very bright central star-forming regions, and these are selected in such a way that is a 0.1 to 0.3 redshift. What we wanted to look for in this is what is called the extended UV emission. And as you know, the extended UV emission, one of the major science results from Galaxies, which is for the local spiral galaxies, have extended UV emission beyond their optical boundary. And often this optical extended UV emissions are clumpy, so you don't see actually the optical counterpart to those UV blobs. So we selected in such, and of course, these XUVs are a very good way to understand the gas accretion and the low density star formation in the outskirts of the galaxies. So I'll quickly show the results that we have here. What you see here is the FUV image. It's in the far ultraviolet band, and this is the optical boundary. And this is the HST, the same galaxy in 435 bands, the blue band. And this is PSF matched. So the optical boundary is the same footing. And what we see here, these two clumps, which is at a signal to noise about 4, and their magnitude about 25.3 and 25.1. And these are about 10 to the 6 solar mass clumps, which is just outside the optical boundary. And this is the 3 signal to noise FUV boundary. So this came last month, 2 months ago, published in Nature, and these are the 2 external collaborators we had. Sorry, Bruce Almagrin and Francois Combs. So we did a surface brightness profile, and this is one of the interesting point, I thought. we'll go. This is the FUV surface brightness profile. And what we do is, you can see that we go about 28 magnitude at a 3 signal to noise ratio. And this what we do from this observed, we use the PSF and estimate the intrinsic surface brightness profile for these galaxies. And then we define the quantity from here. You can see here, this is also the optical and the UV. So we estimate the intrinsic scale length of this optical and the UV surface brightness profile. And we estimate their ratios here. And when the ratio is greater than 1, and we also estimate the amount of light that is between the PSF convolved optical boundary and the FUV boundary. So we estimate the total light, the XUV light basically. And we see that about of the 14 BCDs, we have 10 cases, we have extended UV emission in this part. And with this, of course, like, we can go up to a very low star formation rate density. It's a great tool to actually look for this stuff. We did quite a bit of analysis on taking an empty patch of sky and try to understand if there are noise peaks or not. So we validate this part, that the clumps that we detect, they are actually not noise peaks, but they are real. These are like a bit of a calculation, because we just estimated that if these clumps are in the outer part of the optical boundary, how much time they would take to go inside. And we estimate the time scale using the dynamical friction, and some reasonable estimate shows that it's a reasonable way to grow these blue compact dwarf galaxies actually. And in future, we are doing a mosaics of the entire UV covering the entire Chanda Deep Field South. And this is more than about 100 kiloseconds of data will be available for looking in the UV. So I'm close to the end, and thank you.
Thank you very much.
Yeah.
You have any questions?
Thanks, Kanak. So my question is, how much of the UVIT fields are going to be covered by, let's say, the early LSST fields? Do you know?
Oh, sorry, it's gone. So as far as I know, I don't have a proper number, but I know that we have on the good the south, Chanda Deep Field South, the entire Chanda Deep Field South, plus there are some neighboring like sky around the Chanda Deep Field South. Each of them 28 arc-made diameter. So I had some collaboration from people in Australia. So they wanted to look at the Devil's Field. So the Devil's Field, the 3 fields observed in using the Chanda. So in and around the Chanda Deep Field South, I should get the numbers.
Should be LSST
yes.
imaging.
Yeah.
So there is a question in Slack. I cannot read it. It's not Nushkia. Oh, okay. I think there is.
Okay, so there's a question from Nushkia. Could you clarify what is the physical scenario creating the extended UV light in these galaxies and not other galaxies? So what is the physical mechanism that produces the XUV disks, I guess?
It's truly speaking, it's a very, I think it's a difficult question to answer. All we understand is that this XUV clumps that we see, we do not have optical counterparts. So we do not know what is underneath them. And that is probably stopping us to answer it directly. So one could be that the gas inflow, and they condense and probably create this very blue FUV clumps, because you can no, I cannot see, but they're actually very blue. So I think we are lacking. What we're lacking is to answer this question is like if there is all stars somehow could be seen, and then that would actually clarify this part. Yeah.
And actually, we don't have time. I think they want to leave. Can you discuss afterwards? Yeah, two questions. Okay.
Sure.
Thank you. Let's thank Kanak again. And we have last talk is by Nushkia Chamba, and she will speak in remote. I don't know if she's there or not. Are you
Yeah,
there?
I'm here. Can you hear me?
Fantastic. So they are setting the screen. Let us know if you see everything right.
Yeah, Nushkia, can you share and then just?
Oh, somebody else has already shared it, but that's not me.